Assalamualaikum warahmatullahi wabarakatuh, and greetings to everyone that's watching this video. First of all, let me introduce our group members. For me, my name is Ahmad Iman Hakim bin Muhammad Arif. My group members are Ahmad Fitri bin Amar, Muhammad Halid bin Cik Hassan, and Adli Zaim bin Muhammad Fitri Izwendi. Today, we will be presenting our project on the design and fabrication of a Pmos Mosfet using a PBL, a project-based learning approach. In general, Mosfet is one of the most important components in modern electronic circuits. In our case, we focus on the Pmos type, which uses holes as the main charge carriers. Pmos devices are widely used together with NMOS in CMOS technology to achieve low power consumption and efficient performance. This project mainly focuses on understanding how a Pmos MOSFET is fabricated on a silicon wafer through several microfabrication processes. Now, moving on to the abstract of our project, this project presents the design and fabrication process of a Pmos MOSFET during standard semiconductor fabrication techniques. The process starts with surface preparation on the silicon substrate, following by oxidation to form a silicon dioxide layer. Next, photolithography is used to transfer the desired pattern onto the wafer. Then etching is performed to remove selected areas, and the diffusion is carried out to form the source and drain regions of the Pmos devices. Finally, metallization is done to create electrical contacts, completing the device structure. Overall, this project highlights how each fabrication step plays an important role in determining the performance, reliability, and efficiency of the Pmos MOSFET. That's all from me. I'll pass it to my friends.
The next one, we are going through the introduction. MOSFET is a key component in the modern integrated circuit due to its low power consumption, high speed, and scalability. Its fabrication involves several critical microfabrication processes on a silicon substrate, including oxidation, photolithography, etching, diffusion, and metallization. Each step is essential in defining the device structure and performance. This project applies a project-based learning or PBL approach to understand the design and complete fabrication process of a MOSFET, highlighting the importance of precision and process control. Then we are going to move through the process that we need to do to get the final product. Based on our IntelliSuite simulation, this process, the process shows how a raw silicon material is transformed step by step into a functional electronic structure. It involves several important techniques that I have said on the introduction. Each step plays a critical role, and all of them must be carefully controlled to ensure the final device works properly. For our component, there are 23 steps, but not all of the steps are going to be mentioned as it is repetitive and most likely to be redundant. The first one, the fabrication process begins with a Chorosky process, which is used to produce a single crystal silicon substrate. In this process, high purity silicon is first melted at a very high temperature. Then a small seed crystal is dipped into the molten silicon and slowly pulled upward while rotating. As it is pulled, The silicon cools and solidifies, forming a large cylindrical crystal called an ingot. This ingot has a very uniform atomic structure, which is extremely important for semiconductor device. After that, the ingot is sliced into a thin wafer, and these wafer are used as a starting substrate for our fabrication process, or as our base. Next, as we can see on the poster, we are going through the first oxidation. A layer of silicon dioxide, or SiO2, is formed on the surface using thermal oxidation. This process involves exposing the silicon wafer to oxygen or steam at high temperature, allowing an oxide layer to grow on the surface. This SiO2 layer is very important because it acts as an insulating layer, a protective barrier, and also a masking layer for future steps. After oxidation, we apply a photoresist layer, specifically PRS 1800, using a spin coating method. In this process, liquid photoresist is dropped onto the wafer and spun at high speed from a thin and uniform coat to form a thin and a uniform coating. This layer is sensitive to ultraviolet light and will be used to transfer pattern onto the wafer surface. The next one is lithography process, where we use UV light and a mask to define patterns. The wafer is aligned with the mask and exposed to UV light. Depending on the exposure, certain areas of the photoresist will remain while others are removed. This step is extremely important because it determines the shape and layout of the device. After lithography, we perform etching to remove unwanted materials. There are two main types used in this process. Dry etching, or RIE, is RIE, which use plasma to remove SiO2. Wet etching is use chemical solution to remove photoresist. This step transfer the pattern from the photoresist into the oxide layer, creating the required structure on the wafer. The next, the other process will be explained by my fellow friends. That's all from me. Thank you.
Okay, so for step 6, after lithography, we perform etching to remove unwanted materials. There are two main types used in this process, which is dry etching, RIE, which uses plasma to remove SiO2, wet etching, which uses chemical solutions to remove photoresist. This step transfers the pattern from the photoresist into the oxide layer, creating the required structure on the wafer. So for doping, we use P-type diffusion. In this process, impurities are introduced into the silicon to modify its electrical properties. These impurities can create regions with different conductivity. This is very important because it forms the active regions of the device, such as source, drain, and channel regions. Without doping, the silicon would not function properly in electronic applications. For oxide etching and deposition, part of the oxide layer is removed using wet etching, especially BOE. Then a new SiO2 layer is deposited again. This step helps to clean the surface, prepare for the next patterning process, ensure better layer quality for the further fabrication. For the second lithography and etching, process of photoresist coating, lithography, and etching is repeated again. This allows us to create more detailed patterns and open specific areas where electrical contacts will be formed later. Repeating these steps improves the precision of the device structure. For the metallization, where aluminium etches AL, is deposited using a process called sputtering. This creates a metal layer on the water surface. After that, photoresist is applied again, lithography is performed, the aluminium is etched. This forms the metal interconnections which allow electrical signals to flow through the device. For the final metal layer formation, another aluminium is deposited and patterned. This ensures that all connections are complete and that the device can function properly. At this stage, the structure of the semiconductor is fully formed.
Next, I will conclude for this topic. In conclusion, the semiconductor fabrication process is a precise and well-controlled sequence of steps that transform a raw silicon wafer into a functional electronic device. Starting from the Chorosky grown substrate, the wafer undergoes oxidation, lithography, etching, doping, and metallization. Each step plays an important role in defining the structure, electrical properties, and connection of the device. Any small error in these processes can affect the overall performance. Overall, this process highlight how advanced engineering techniques are used to produce modern electronic components, showing how a simple silicon wafer can be developed into a complex and highly functional device. That's all from us. Thank you.